Welcome to the Explainer. It's kind of wild to think about, but what really connects a tiny little aphid to a huge soaring eagle? Well, today we're going to pull back the curtain on this incredible, invisible web of energy that links literally every living thing, from a single blade of grass all the way to the biggest whale in the ocean.
All right, so let's kick things off with a really big question. You look outside and you see all these different creatures, right? Big ones, small ones, all interacting in these super complex ways. But what's actually powering all of it? What's the fundamental source of energy that keeps the whole show running? Okay, so here's our game plan. We're going to start with the engine of life, then move to the great food chain, meet the all-important cleanup crew, untangle the reality of the food web, and finish up with a universal rule that basically governs everything.
All right, first up, let's dive right into our first building block. And these are basically the power plants for every single ecosystem out there.
So these are what we call producers, or if you want to get technical, autotrophs. And that name is perfect because it literally means self-feeder. These guys are the absolute foundation of, well, pretty much all life as we know it. Why? Because they're the only ones who can make their own food from scratch, using simple, non-living stuff. The most famous way they do this, of course, is photosynthesis, taking sunlight and turning it into pure chemical energy.
But here's the thing that's so cool about producers. They do way more than just make food. Seriously, think of them as the engineers of the ecosystem. They help regulate the water cycle. They literally balance the air we breathe by sucking up CO2 and pumping out oxygen. Come on. Plus, they create homes for countless other creatures, and their roots hold the soil together. They're just crucial.
Okay, so the producers are busy making all this energy. The next logical question is, who eats it? And that, my friends, brings us to the consumers.
Right, so unlike the producers, these guys, the consumers or heterotrophs, can't make their own food. Hetero just means other, so they have to get their energy by eating, well, other things. It's the only way they can get the fuel they need to survive.
And boy, have consumers gotten creative. There are all kinds of strategies for getting that food. You've got your classic herbivores just munching away on plants. Then there are the predators, out there hunting other animals. You've got sneaky parasites that live on a host. And of course, the scavengers, who are cleaning up what's left behind. Every single one has a really important job in keeping that energy flowing.
So the simplest way to picture this energy flow is with something called a food chain. Just think of it like a straight line, a single path for energy to travel. And the most important part of these diagrams, the arrows. You got to pay attention to the arrows because they always show you where the energy is going, from the thing being eaten to the thing doing the eating.
So check this out. Here's a super classic example. The energy starts in the grass. That's our producer, trophic level 1. Then a rabbit comes along and eats the grass. That makes the rabbit a primary consumer, and we're now at trophic level 2. Next up, a fox eats the rabbit, becoming a secondary consumer at trophic level 3. See how that works? Each step up the chain is a new trophic level. And right at the very top, you'll find the apex predator, the boss who doesn't have to worry about being hunted. Okay, but wait a minute. What happens when things die? A producer, a consumer, an apex predator, they all die eventually, right? Well, that's where this absolutely critical and honestly super overlooked group comes into play, nature's cleanup crew. Now this cleanup crew, the decomposers, they're basically split into two main teams, and the biggest difference between them is how they eat. On one side, you have the detritivores, like an earthworm. They have mouths and they digest stuff internally, inside their bodies. But then you have the saprotrophs, think fungi and bacteria, and these guys do something wild. They don't have mouths, instead they release these special enzymes to break down their food outside their bodies, and then they just absorb the nutrients. How cool is that?
So here's the bottom line. Without these guys, ecosystems would literally grind to a halt. We'd be buried in dead stuff. They're not just tidying up, they're preventing diseases from spreading, and this is the most important part, they recycle all those vital nutrients right back into the soil. That's what allows new plants to grow and the whole cycle to start over. They are, without a doubt, nature's ultimate recyclers.
Okay, so we've got our basic pieces, right? Producers, consumers, decomposers, all in a nice, simple chain. But you've probably already guessed this, nature is almost never that neat and tidy.
Look, that simple food chain idea, it's a great starting point, for sure. It helps us get the basics down, but it doesn't even begin to show the whole picture. The reality of how ecosystems work is way more complex, way more interconnected, and honestly, way more fascinating.
So, to really see what's going on, we need to zoom out. We need to move from the simple food chain to the much more realistic food web. And you can see right away why a food web is so much more accurate. In the real world, animals are not picky eaters that only eat one thing. A fox isn't just eating rabbits. A sparrow isn't just eating caterpillars. They eat lots of different things. And this creates this incredibly complex, tangled network of connections that looks exactly like a web.
And what these food webs show us so clearly is this critical idea of interdependence. Everything is connected to everything else. So let's play a little game. What happens if we just pull on one of those threads? Let's say, in this web right here, all the earthworms just disappeared. Poof, gone. What happens next?
Well, for starters, the grass would probably have a great time. With fewer things munching on it, its population would likely explode.
But on the other hand, for the frogs and mice that depend on earthworms for dinner, it would be a total disaster. Their populations would crash hard.
And that right there is interdependence in a nutshell. You take out one seemingly small piece, and it sends these massive ripple effects through the whole system. It's the perfect proof that, in nature, absolutely nothing exists in isolation.
All right, it's time for the final piece of our puzzle. In this one, this is a fundamental rule of physics that shapes literally all life on Earth.
Okay, so think about this for a second. Why aren't food chains super long, like 10, 15, 20 levels deep? Why don't you have a predator that eats another predator that eats another predator, and so on and so on? What stops it?
Well, the reason is actually pretty simple, but it has huge consequences. It's because transferring energy is, well, it's really inefficient. Here's the rule of thumb. Only about 10% of the energy from one trophic level actually makes it to the next one. 10%? The other 90%? It just gets lost. It's like there's a universal energy tax, and every single living thing has to pay it.
So where does all that energy go? Well, it's a few things. First, not every part of an animal or plant gets eaten, think bones or stems. Some energy is just lost as waste. But honestly, most of it is just used. It's the energy the organism burned just to live its life, to move around, to grow, to keep its body running. And a massive chunk of it is just lost as body heat, radiating out into the environment.
So when you put it all together, you realize that ecosystems aren't just these random collections of animals and plants. No way. They are these incredibly intricate, deeply interconnected webs that are governed by the strict laws of energy. That's why food chains are short. By the time you get up to the 4th or 5th level, there's just not enough energy left in the tank to support anything else. And that leaves us with that one big critical thought to chew on. If you pull on just one of those threads, how much of that beautiful, complex web really unravels?